Hey there, I'm Antoine, and I've been working with our team here at Great Scott Gadgets on developing Cynthion, our new tool for exploring and experimenting with USB. Today we're going to take a look at an example of how you can use it to prototype a high-quality USB audio interface. We'll be using Synthion's Lattice ECP5 FPGA, the Luna USB gateware library, and the Amaranth HDL language for our implementation. We'll also be covering topics around USB Audio Class 2 devices in general. It's quite a deep topic, and our video can only be so long, so we won't be covering that much about getting started with Cynthion USB or FPGA development. If you would like to learn more about these topics, I've linked some resources that can also be found in the description below. Finally, the gateware and slides for this video are available in a GitHub repository, which you can also find in the description below. So without further ado, let's dig in. So if we want to implement UAC2, we probably need a bit of an idea of what it looks like. The canonical overview and specification for USB Audio Class 2 devices can be found in the specification documents. These are available at usb.org, freely available, and there are three of them. The first is audio devices, and that's the big one. It contains the high-level view and descriptor specifications and basically how everything fits together. The second one is audio data formats. In practice, usually audio interfaces are just sending PCM data, PCM encoded data over, but there are other options if you want to get experimental, and this document covers them. Then we got the terminal type spec, and these are abstract definitions that UAC uses to describe the audio interface, the sources, the sinks, the controls, the functions, and so on. But I'm not going to do a read-through of the spec. In fact, I think a much easier way to get an idea of what's actually going on the wire is to actually look at what's going on the wire. So I've got a USB Audio Class 2 interface here, and on top of it is a Cynthion running the analyzer gateware. You can use this to sniff the traffic between the host and the audio interface. So to connect it, we start by plugging the machine running the packetry software, which we use to actually look at the capture traffic, into the control port. Then we can plug the interface itself into the target A port, and finally the host into the target C port, but we can hold off on doing that because we want to capture the enumeration of the device. And to do that, we've got to start packetry running first. So let's open up packetry and we start a capture. And now when we plug the host in, we should see, there we go. We can take a quick look at it. There's a device descriptor, which is pretty much what you'd expect. Product string, manufacturer string, got a configuration, specifically the one we're interested in is the audio function. And of these interfaces, we've got this one, which is got an in isochronous endpoint. This is sending data from the device to the host. And then we got this one over here, which has got two endpoints. First, the out isochronous endpoint, which is going from the host to the device. And then another in isochronous endpoint, which is the device sending feedback to the host to assist with synchronization of the audio. But what we need to do now is we need to send some audio from the host to the device and see if we can capture it. To do that, I'm going to start a VCP rack, and you'll see we are generating two sine waves. One is a 500 Hertz and the other one's a 5 kilohertz. And let's route that to our audio interface and then select the audio interface. And And there you can see data has just started going through. And if we look down here, we'll see, okay, here we got our asynchronous transfers on the in endpoint, the out endpoint, and then going slightly slower than the others is the feedback endpoint, which we'll talk about more later. And we are capturing our sine waves going over the wire. So let's stop packetry and save this. And then let's shut down VCB rack and get ourselves a terminal open. Okay, what do we got here? Cool, we got 28 meg file. What does it actually look like? Let's just format it in hex mode. And okay, a lot of zeros. Oh, and there it begins. Okay. So this is just the raw binary data. It's in the audio stream format for USB audio class. So if we want to actually do something with it, we're going to have to convert it. So luckily I've already written a little script that can do that for us. Basically what it does is it opens the file, and while there's file to read, it reads a byte and discards it, and then reads another 3 bytes. And the reason for this is that this interface is configured in 24-bit mode, but it sends data as 32-bit words, which means that the first byte of every frame is just a padding byte, so we can just discard it, read it, and read it all into our array, and then we can open a file with a WAV module and basically save this as a WAV file, which most software can read. So let's run that. Browse it, and then we got our WAV files, slightly smaller because we're formatting the WAV samples as 24-bit rather than the 32 bits that we captured. And let's open up Sonic Visualizer, which is a very fine piece of open source software for working with audio files. And what have we got here? We got our capture, and oh, we definitely got something here. Let's zoom in a little bit. And yep, that looks like 2 sine waves. Let's quickly just check that it's actually got the data that we expect. We do a FFT, and yep, we got one peak at 500 Hz for the first wave and another one at 5 kHz for the second wave. So yeah, it's pretty simple. If you look at UAC in this way, you've got the descriptors, which are specified in the specification. You've got to implement those. And then you've got 3 endpoints that are actually transferring the data. And do those, and we should be able to build an audio interface. Let's give it a go. So we're going to start off just by setting up the basic boilerplate for our USB device. And to get going, so we're going to create a new Amaranth component called USB Audio Class 2 device. It's got a couple of arguments on the constructor. It'll take a sample rate, bit depth, how many channels it has, and what the actual physical interface bus is. We've got a top-level initialization here. Later on we will add the components ports onto that, but for now we can leave it empty. And then next we got the elaborate method that defines the gateware for this component. So the first thing we always do in the Amaranth component is we create a module, and then we're going to create a Lunar USB device, which refers to the target PHY physical interface on Cynthion. We'll be passing that in through the constructor. And we're going to connect our device as a high-speed device. And then we're going to add a standard control endpoint. And we've got a little method here, descriptors, self-create descriptors, down here below. We're basically going to take a device descriptor collection. The next step, we're going to populate that, but for now, we're just going to pass an empty one. And then we add a control endpoint. And then to that control endpoint, we can then add some standard request handlers. We're going to pass in our device descriptor collection. And then we're also going to have a skip list because our audio interface has multiple interfaces, and Luna doesn't deal with multiple interfaces by default. So we're going to have to handle those ourselves in our request handler later. So basically all that the skip list does, it sends in a little lambda that says if it's a standard request for set interface, don't handle it, we will handle it ourselves. Okay, and that brings us to our next bit. We just need to create a top level for our gateware. Let me just walk you through that. It's very simple, just a Amaranth elaborate level. We'll call it top as that's the entry point for our gateware. We define some default clock frequencies. These are the default Cynthions. It's got a fast clock, a sync clock, and a USB clock at 60 megahertz. We're going to be doing everything today, the USB clock. And then we can set the parameters we're going to be using for our USB audio device. We're going to work, for the purposes of this video, we're going to work at 48 kilohertz, 24-bit depth, and 2 channels. And then we do our Amaranth elaborate, where we just generate our clock domains and resets with the platform clock domain generator. And then we instantiate the actual USB audio class 2 device that we've just defined in the previous file. And you'll see the bus is we're doing a platform request for Cynthion's target 5 port. And then in the main, we just set the login to debug, and then we call the Luna top level climb method that will take care of building the gateway for us and flashing it to the Cynthion. This should all build already. It won't do anything yet because we haven't got any device descriptors, but you can see that it does build. So let's actually get it to do something. So first thing we want to do is we want to create the device descriptor collection for our standard request handler. And that will contain stuff like the device descriptor and all the various USB audio class 2 descriptors. So the first thing we're going to start with is the device descriptor collection, and then within the device descriptor collection, we're going to begin with the device descriptor itself. So we go down to our create descriptors method. You'll see that this is basically how we define it. So we've got our device descriptor collection, and then we can add the device descriptor to that. And over here we got the normal vendor ID, product ID, manufacturer, product, serial number, etc. And then the important parts is that the device class is set as a miscellaneous device, and the reason for that is because we're actually going to be using the interface association descriptors to define the class behavior. So the IDs here for device subclass and device protocol says to the host that go look at what the interface association descriptor is if you want to know what the device does. Cool. And now that we've implemented the device descriptor, we should at least be able to do a basic enumeration, see it on the USB bus over here. So it won't show up as the actual audio interface yet, mainly because we only got the device descriptor. We still need to have the configuration descriptors and everything else to add to it. So you'll see there's our device so far. Cool, now we have the simplest possible thing that will even slightly enumerate. We can now get into the nitty-gritty. And the very first thing we want to do is we want to define the configuration descriptor. And that is going to contain all the other descriptors that the host needs to know that it's a USB audio class device, what its capabilities are, and so on. So let's begin. We create the configuration with the configuration descriptor method on the device descriptor collection, and we add the interface association descriptor. We've got 3 interfaces. The first one's the audio control interface, then audio from the host, and then audio to the host. That means we can now get started on interface 0, and that's quite a mouthful, but let's go through it slowly. First thing we do is we add the standard audio control interface descriptor. That's the one at the top, and that just tells us what the interface number is. It sets the function, class, and subclass to audio and control. We don't have to do that. The actual standard audio control interface descriptor from the Python USB protocol library will do that for us. Next, we've got the class-specific audio control interface descriptor. That one is quite straightforward. It basically, we just say it's a class-specific audio control interface descriptor. And here's where things are going to start getting a little bit hairy. If you look at the full thing, it basically contains a bunch of nodes. We've got a clock source descriptor, input terminal, output terminal, another input terminal, another output terminal, and these things have IDs and names and numbers, and essentially what they are is they're an abstract description of what the inside of our audio interface looks like, and it's kind of fun. Before we code this up, let's dig in a little bit and see what that means for us. So basically, it describes a little graph diagram of the connections inside our audio interface. So if you look at the diagram, you'll see that this actually relates to the various elements. So our audio interface provides its own clock. It's an internal clock. It's fixed. It can't be changed. We're going to be running it at 48 kilohertz. And then that clock is an input to our terminals. It drives our terminals. And then if we look at the actual terminals, they come in 2 varieties, input terminals and output terminals. And they've got different types. So looking at the first line, we've got a USB streaming input terminal, which goes to an output terminal, which is just defined as a speaker. These date back to kind of the early days of USB audio class 1, where you had speakers and microphones because they were self-contained units. But for now, we assume the speaker is the output of our audio interface. So this USB streaming port is basically that is the data that's coming from the host, and that is going to the output on the audio interface. And then similarly, we've got an output terminal of USB streaming type, which gets its data from the microphone on the USB audio device. So these USB streaming endpoints, this is what's carrying the actual streaming data on the wire, and the speaker and the microphone are sort of physically what they're connected to. And then here you can see is how the descriptors actually map to that, is they got IDs, and then like you've got an input terminal, and it's got a clock source ID, and its IDs too. You've got an output terminal, which is the speaker. It's got a clock source ID of 1 and a source ID of 2, which is the previous one, and so on. So a little bit abstract, but if you can just picture the layout of stuff inside it, it's actually quite straightforward and simple. So now we can code these up. So let's do that. We're going to have our various terminals. We've got the clock source, and it's defined as an internal fixed clock. Frequency control is read-only, the host can't set it. We've got the input terminal from the host going to the USB device, which is of type USB streaming, and it's got 2 channels. Terminal ID for that is 2, and then we've got the output, audio output terminal to the USB device's speaker output, which has got a terminal type of speaker, a source ID of 2, so the source is this one over here. And again, the clock source ID is the clock source at the top. And then similarly for the audio input terminal from the USB device's microphone input, it's got 2 channels, and that is going into the streaming output terminal to the host from the USB device. So that very simply is your audio control interface. And it just specifies the layout of the USB device. Next thing we're going to get to is interface 1, which is our audio streaming interface descriptor. And these are interesting because we got 2 of them. We've got interface 1, and then we've got interface 1 alt 1. And the reason for that being is that these audio streaming interfaces have 2 possible states. One is a quiet state, when it isn't actively streaming audio over the wire, and that's the first one. And then it's got another one when it is actively streaming, and that's just a way for the system to conserve resources when the device is not in use. And the first one you'll see is basically straightforward, no data definitions attached to it, and the second one suddenly goes quite a lot more in depth, and you can start seeing things like the format for the streams and bit depths and so on. But without further ado, now we can get to interface 1, and that's our audio output from the host to the USB device. And we're going to start off with the first interface descriptor, which is the alt-0 setting for when the interface isn't active. And you see we just give the interface number and we say alternate setting 0. The next one is the active setting, and that one is a little bit more complicated. It's got quite a lot more going on. So we begin with the active setting. Let's go to interface number 1. We set the alt setting to 1. And first thing you'll notice is it's got 2 endpoints versus the quiet setting, which had none. It had no endpoints whatsoever or anything following up from it. And then let's have a look at the descriptors that hang off this. So the first one we've got is we got the class-specific audio streaming interface, and that tells us a format type, which is format type 1. Type 1 formats are formats that aren't compressed, they're just encoded. Type 2 and 3 has support for things like compression. The actual format we're using is pulse code modulated data, PCM, and it's got 2 channels. And then here's quite fun, you'll see it's got a terminal link ID over here, and you'll be correct if you think that this refers to our first interface, which defined a streaming input terminal. It actually refers to the terminal ID over there. And that tells the host that this interface provides the streaming for that. So then we got the type 1 format type descriptor, and this tells us a couple of things. It tells us what the bit resolution of our data is, and then it's also got something called subslot size, I'm not going to define that now. We're going to get into that later when we talk about the framing formats. But for now, we can just set it to a constant value of 4 bytes. And basically that is, we're going to have 24 bits of data that's going to be squeezed into a 32-bit subslot. But I'll talk more about that later. And then we got the endpoint descriptor that's actually carrying the audio outstream. It's a out endpoint, isochronous transfer. It uses async synchronization, much more about that later, and the usage type is data. It's got a max packet size of bytes per microframe plus 1. Again, I'm not going to talk about that quite yet. We'll get to that later. For now, I'm just going to set it again to a fixed value, just so that we can compile it and test it. And then it's got a max, it's got an interval of 1, and what that says is that the host is going to query it once per microframe, but we'll talk more about that later. And then we again just mark that as the isochronous audio data endpoint, and then we got the second endpoint, which is the synchronization endpoint. And what that's responsible for is making sure that the audio in the device and the host are synchronized. We'll cover that later and talk more about that. But for now, all you need to know is it's an isochronous endpoint, and it's got a max packet size of 4 bytes, and it happens every 4 microframes. And that brings us to our last interface, interface 2, which is basically the same as interface 1, with the exception that this is audio going to the host from the USB device. It's pretty straightforward, pretty much the same as the other one, except the direction's different. And you'll also notice it hasn't got a feedback endpoint because it's taken care of by the other one. Cool, and now we should be able to build that and upload it again. And this time we should be seeing a whole lot more when we look at the bus. Okay, so there's our tutorial. It is showing up. Let's look at it in more detail. And there you'll see is all our descriptors now. So it's not quite enough yet to show up as a USB audio device on the host, but we're very, very close. All we need to do at this point is add a few request handlers, that we'll do next. Okay, now that we've got our device descriptors down, the next 2 missing pieces we need to add before it'll actually show up as an audio interface on the host is we're going to need to add the request handlers. We got 2. We've got the main one, which is the UAC2 request handler, and then we also got a little utility store request handler just to handle any requests that we don't support. So let's implement those. Okay, so first we want to go to our class device elaborate method, and we can add them there. So we're going to attach a class request handler, which we'll define next. And then we also just got our store request handler saying that if there are any vendor reserved requests, to stall those because we don't have or need any for what we're doing. So the next big step is going to be to actually define our UAC2 request handler. So let's get to that. To do that, let's create a new class. And basically what this is going to be It's going to be a subclass of Luna's USB request handler, which gives us the core functionality to handle requests. We're going to just set the sample rate here, save that, and call the superclasses constructor. And then we want to implement the actual gateware for this. So this is like all Amaranth modules. We create a module and return at the end of it. So this can get a little bit hairy, but let's try and walk our way through it. First, we just do a couple of shortcuts to the underlying interface, USB interface in Luna, and for the setup interface. Then we also need to set up a transmitter to be able to send data in response to requests. And this is just a simple stream serializer that can take X amount of data and then stream it out over a USB in stream. And then also quite important that it's running in the USB domain. Next thing we want to do is let's create a few more shortcuts for the actual requests we want to handle. So there's going to be a standard request for set interface, because remember we've got the client and the active interfaces, and we need to handle the request when the host wants to switch between them. So those are setup type is a standard, recipient's interface, and request to set interface. Then we also got some UAC2 requests. So these are two types of UAC2 requests. UAC2 requests could ask for a range of values, or it could ask for the current value for something, for parameter. And then we've got a particular parameter, a request clock frequency, that the host is going to be asking using these two methods, the request range and the request current value. Okay, the next bit, if you've done any of the other Cynthion gateway tutorials, this should be familiar to you. So I'm not going to go too deep into it. I'm just going to breeze through this. So the first request we're handling is the standard request for set interface. So basically you have to claim an interface, and then you just act the data out and you say, hey, I got it, and then you accept the request. Then the next one, we're gonna handle the request range for request clock frequency. So the host is basically going to ask what's the range of supported sample rates for this audio interface. And again, same story, claim the interface. And now we're going to use our transmitter that we did at the top. And basically, we will then format it as a range. And there's only one subrange, and it's got a minimum value of sample rate and a maximum value of sample rate because we're only supporting one. If you supported multiple interface frequencies, you would add them to the list here. And then respond once the data is requested, and then act the status stage at the end of it. Then we also got one final request left, which is when the host wants to know what the current clock frequency is. And that's also pretty simple. Claim the interface attached to the transmitter, and just send the data containing the sample rate back. And then finally, we also want to stall any unsupported requests, so the host doesn't hang around waiting for something that we can't do. And that is pretty much that. It's long, it's spidery, but it's very straightforward. We're handling 4 different requests. We're handling a set interface request. We're handling a request range for the interface's clock frequency. We're handling a request the current value of the interface's clock frequency, and then we're stalling unsupported requests. Okay, and now that we've got this, there's every chance that if we now build the gateway and upload it to the device, that it should actually enumerate as an audio device. So let's just quickly pull up the audio device list, and let's see what happens. And we are building, and we are building, and uploading, and there we go. We have got a USB audio class 2 device. It doesn't actually do anything yet. We've still got to add the actual endpoints to the gateway and figure out how to send data across those endpoints. But our first major milestone is in place. We have managed to convince our host that Cynthion is a USB audio class 2 device. And this brings us to the end of part 1 of USB audio from scratch. In the second and final part of this video, we can implement the gateway to stream audio between our audio interface and the host. You can find the link in the description below. If you enjoyed this video, please hit like and subscribe. This is Antoine for Great Scott Gadgets, signing out.